Okay, sorry about that. We had some technical issues. So sorry getting started a little bit later than normal. But so the first part we're going to go over today is we're going to look at some questions from quiz 4. And we will hopefully have that finished grading for you all by Friday. So sometime tomorrow you should expect to see um, your quiz results back on that. So we're just going to go over some problems from that. So here's problem 4 from quiz 4. And so for this problem, we were asked to look at this relation on the set A, where that's made up of the letters A, B, C, D, E. And then we're supposed to decide based on all of these 6 relations, which of them are reflexive, symmetric, antisymmetric, transitive, or which of them don't have any of the properties. So let's take a look at this first relation. And so let's see, is this relation reflexive? So what does it mean to be reflexive? Well, it means that for all A, B, C, D, E in the set A, we have A, B, B, C, C, D, D, E, E. So we can see, yeah, this is a reflexive relation. Is it symmetric? So for all A, B, is B, A in the relation? And that actually is true for this relation. It's primarily true because there is no such AB in the relation, so we don't need to have like a BA. It just holds. So similar for antisymmetry. This relation is also antisymmetric for a similar reason, because there is no such AB in the relation. And also for similar reason, this is a transitive relation, because we don't have any such AB and BC for us to be required to have AC. So this just holds. And this is actually, this relation is basically an equality relation, where we only have A, B, B, C, C, D, D, E, E. And this is the only relation that has all 4 properties. That is all reflexive, symmetric, antisymmetric, and transitive. If you look at R2, we again have reflexivity because R1 is unioned with this set. And then now we have to decide, well, do we have symmetry? And yes, we do. DB is in the relation, or BD is in the relation, and DB is in the relation, AE and EAR, so it's symmetric. It's not antisymmetric because for BD there is DB in the relation, so it's not antisymmetric. And it's transitive, similar for the explanation used in part A. If we look at part C, again, we have this as reflexive because R1 is union with it, and R1 was already reflexive. Is it symmetric? Well, for it to be symmetric, we have BA in the relation. We need AB to be in the relation. AB is not in the relation, so this is not symmetric. And then to check antisymmetry, we have to check for all such pairs that the flipping of them is not in the relation. So AB is not in the relation, BC is not in the relation, AC is not in the relation, and AD is not in the relation. So this is antisymmetric. And this is also a transitive relation. Why is it transitive? Well, because we actually, the only thing we have to check here is, so CB is in the relation, BA is in the relation, and CA is in the relation. And that's required from transitivity. And then if you did that with all the other pairs, you would also see that it's transitive. R4, it's not reflexive because it doesn't have AA in the relation. It's not symmetric. It doesn't have BA in the relation. It's not antisymmetric. CD is in the relation and DC is in the relation. And then this one is not transitive. Because CD is in the relation and DC is in the relation, but CC is not in the relation. So it doesn't meet the definition of transitivity. So for this one, it's none. A cross A. that'll be reflexive because this will have all of the pairs in the cross product. So it'll be reflexive because of that. It'll be symmetric because of that, and it'll also be transitive because it'll contain all such pairings. And then for R6, it's not reflexive. AA is not in the relation. We can check if it's symmetric. BC is in the relation and CB is. AD and DA are in the relation, so it's symmetric. It's not anti-symmetric because CB is in the relation and BC is in the relation. And then it's not transitive. AD is in the relation, DA is in the relation, but AA is not in the relation. So this is just symmetric. So are there any questions for this first part on any of these relations and why all of these are correct?
I guess on the first couple, like in the formal definitions of like the reflexive, symmetric, anti-symmetric, and transitive, it says like for all A, and like on B, there's nothing symmetric for C, but yet the whole thing is still symmetric. I guess I'm kind of confused about that.
Oh, yeah, really good question. So yeah, so what symmetric says is for all AB in the relation, if AB, or for this will be in the set A, if AB is in the relation, then BA is in the relation. And so notice for symmetric, we're requiring if this happens. So in R2, for example, there is no nothing that has like say C comma A. So we don't care whether or not AC is in the relation because this first condition didn't happen. So symmetry just says if this is a pairing in your relation, BA has to be in the relation. So for all pairs we have in our relation, AE is in the relation, EA is, BD and DB is. And that's why it's symmetric, because we just care about the pairs in the relation, not necessarily all such pairings that could have happened.
All right, thank you.
Yeah, no problem. Any other questions on this first part? Okay, awesome. So now let's go to the second part. So we're supposed to figure out which one of these relations are the following. So which one is a function? Well, for a function, we have to have every element of our domain mapped to one and only one element of the codomain. So what does that mean? Well, that means that A, B, C, D, and E need to be mapped to one and only one place. So that happens in R1. A is mapped to A, B is mapped to B, C is mapped to C, and so on. So R1 is a function. R2, not a function. A is mapped to two places. A is mapped to A, and A is mapped to E. And that can't happen with a function. Same thing with R3. B is mapped to B, but B is also mapped to A. So not a function. R4. R4 is not a function. And the reason is E is not mapped to anywhere. It's an element of our domain, but it's not mapped to anything in the codomain. So R4 is not a function. R5 is not a function because each element is mapped to multiple places because it's the cross product. And then R6, not a function. B is mapped to B, and B is also mapped to C. So not a function. So just R1 is the only function among these relations. Yeah, no worries. Yeah, no, yeah, E, yeah, no worries. There were a lot of people forgot about E in R4, that because E isn't mapped anywhere, R4 is not a function. What about, so partial orderings? So can anybody remember what three properties, you can just use the abbreviations here, what three properties are required for a partial ordering? Yeah, so it's got to be reflexive, antisymmetric, or transitive. So R1 is reflexive, antisymmetric, and transitive, and R3 is. So those are the two relations that are partial orderings. And then for equivalence relations, we need reflexive, symmetric, and transitive. So that's R1, R2, and R5. So are there any questions about this second part? Okay, awesome. Let's go to the next problem. So this was problem 5 on the quiz. So we were given this relation, and then we're supposed to prove that this is reflexive and transitive, and then show that this is not antisymmetric. So let's do reflexivity first. So what do we have to show for it to be reflexive? Well, we have to show that basically for all x, so we need to show for all x in Z, that x comma x is in the relation. So this is what we want to show. And then it's reflexive. So let's let's call it A be an element of Z. Then let's look at, to see if this is in relation, let's look at what A plus A is. So then A plus A is equal to 2A, which is even by definition. So A comma A is in the relation, and thus it's reflexive. So then for transitive, what do we have to show? Well, we have to show for all x, y, z in set of integers, if A, B, and B, C are in R, we need to show that AC is in R. So let's let A, B, C be given, be element of Z, and AB is in R, and BC is in R. That's what we assume for transitive. And then we have to show somehow that AC is in R. Well, let's use this definition. What does it mean that AB is in R? Well, if you're in the relation, that means the sum of your entries is even. So A plus B is equal to 2M, where M is an integer, and B plus C is equal to 2N, where N is an integer just by definition. And then now let's look at the sum of these two. So then we'd have A plus B plus C is equal to 2M plus 2N. So A plus C plus 2B is equal to 2M plus 2N. We want to look at what happens with AC to see if it's in the relation. So we'll subtract the 2B from both sides. That'll be 2M plus 2N minus 2B. And we can factor a 2 out here, so that'll be 2M plus N minus B. And this is even by definition. So thus, AC is in the relation. And so R is transitive. Any questions about these two parts, proving if it's reflexive or transitive? Awesome. And then we have one last part. We need to show that this is not antisymmetric by finding a counterexample. So lots of counterexamples. So for one example, let's just say like many such counterexamples for this. Let's say like 2, 4 is in the relation, because why is it in the relation? Well, 2 plus 4 is equal to 6, and 6 is even. Well, 4 plus 2 is even, equals 6, which is even. So 4, 2 is in the relation. So that's just not anti-symmetric. We just had to show for one pair AB that BA was in the relation. Any questions on that? Awesome. So yeah, so hopefully by tomorrow sometime, we'll have this quiz graded back to you. And then you can stop by our office hours if you have more questions outside of these 2 problems. So let's get started on some probability questions that we're going to go through. And for this first one, we'll do some breakout rooms to talk about this problem. So here we're supposing that we have that Jessica's rolling an 8-sided die and John's rolling a 6-sided die. And we want to figure out what's the probability that John's roll from the 6-sided dice is higher than Jessica's roll. So let me just throw this question in the chat. So that way you can copy it and have it when we go into the breakout rooms. And cool. So we'll spend a couple minutes on this in your breakout rooms. All right, so it looks like everyone's back now. Something that was enough time to kind of think about and get some ideas for this. So would anybody, one of the groups, like to explain kind of what their thought process was for approaching this problem? Any one of the groups want to explain kind of what their group was thinking? Okay, yeah, so someone says, yeah, first count the total number of outcomes. Yeah. So let's so S be the sample space. And let's see what the total number of elements are in our sample space. So N of S, well, the total number of possibilities. Well, Jessica has 8 options. John has 6 options. So there'll be 48 total possibilities that we can look at. And then now let's look at the event. Where John's roll is higher than Jessica's. So what are the possibilities for this? Well, the way we can kind of think about it is let's count the number of ways John could win based upon what Jessica's roll is. So let's say that Jessica rolls a 1. So if Jessica rolls a 1, there's 5 ways that John could beat that roll. He could roll a 2, 3, 4, 5, 6. If Jessica rolls a 2, there's 4 ways. Jessica rolls a 3, there's 3 ways. Jessica rolls a 4, there's 2 ways. And if Jessica rolls a 5, there's 1 way. And if Jessica rolls a 6, a 7, or an 8, there's no way that John can beat that roll. So so the total number is 5 plus 4 plus 3 plus 2 plus 1. And that's 15. So there's 15 total rolls in which John's roll will be higher than Jessica's. So the probability that event E happens, that John's roll is higher than Jessica, is just the number of ways that event can happen divided by the total number of our sample space. So it's just 15 over 48, which if you wanted to simplify would be 5 over 16. So any questions on how we did this problem? Or were any groups thinking something different than what we described here? Awesome. Yeah, so just the approach that you take on a lot of these yeah, lots of dice, lots of ways you can do probability dice, definitely. But yeah, so the way you approach a lot of these probability problems is really just counting. Just count the total number of ways your event can happen, and then just divide that by the total. And generally, that's the technique you want to take to approach these probability problems. So let's do another one. It's a little bit more complicated. So we're supposing that we have a non-negative integer solution to the following equation. And each one of these is selected at random, where each possibility is equally likely to be chosen. And so we're looking at what's the probability that in this particular solution, the variable w is less than or equal to 2. So in other words, there's just 3 options for w. It's either going to be 0, 1, or 2. So let's take a couple minutes to just think about this on your own, and then we'll walk through the solution. Okay, so hopefully that was enough time to get a little bit started on the problem. So let's do how we start a probability problem. Well, we need to count the total number in our sample space. So let's let S be the sample space. So then what is N of S? Someone just wants to type in chat. How do we count the total number of possible non-negative integer solutions to this equation? Yeah, so somebody says, yeah, so this is counting, we're counting a bag. So the way we do it is it's C of, in this case, our R is 10, so 10 plus 4 minus 1, choose 10, which would be C of 13, choose 10, and this is 286 possibilities. Just the standard formula for counting bags, since we have non-negative integer solutions here. So now let's look at event E. So E is the event where W is less than or equal to 2. Well, this event is actually quite hard, is a little bit hard to count. And if you recall from when we were doing counting, on these types of problems, it's often easier to count when W has at least some value than when W is less than some value. So let's count instead E bar. So then E bar is the event where W is greater than or equal to 3. It's the event that contains all other possibilities. And this turns out to be a lot easier to count. So how do we count this? Well, the idea here, right, is let's call the basic idea here is you can take, like, we're then solving where W is at least 3. So we're solving this problem for non-negative integer solutions. And this is W plus X plus Y plus Z equal to nope, scratch that. I was about to explain that completely incorrectly. But the basic idea is if W is at least 3, you can subtract 3 from both sides, and then just find the non-negative integer solutions, where let's call this W prime plus X plus Y plus Z is equal to 7, where W is equal to W prime plus 3. Then the number of ways to do this, to count this, for E bar, well, it's just another bag problem here. And we've got 7 plus 4 minus 1. Choose 7. So that's C of 10, choose 7, which is 120. And then the probability of event E happening, well, what's that? Well, that's just 1 minus the probability of E bar. Either event E happens or it doesn't happen. Yeah, so it looks like, yeah, so somebody else in chat counted the ways. Yeah, so that would have been a perfectly valid way. So what they did is they just said, well, let's consider all the possible values of W. And they counted for when W is equal to 0, 1, and 2. And then, yeah, if you add those up, you should get the exact same, we'll end up with the exact same answer. Just a different way of counting. And in counting problems, there's lots of different ways we can count. But that's often a good way to check if your answer is right, if you can count it a second way, if it works. So the probability of event E happening, we know that's just 1 minus the probability that E bar happens. Because in this case, either event E happens or E bar happens. They're mutually exclusive. And then what's the probability of E bar happening? Well, that's just the number of events of event E bar happening divided by the total. And then this would be, so we'll have 166 over 286, or 83 over 143. And just in case you're wondering, this is approximately 0.5804. So any questions on this problem? Awesome. So it's just a similar probability technique that we used before. Count the total number of possibilities, count the possibilities of your event happening, and then you can just find the probability that way. But sometimes it's easier to find the probability of the opposite of that event happening, of E bar. So now let's move on to this next problem. So here we're considering choosing a committee of 3 people for a club that has 8 sophomores and 12 juniors. And so we're going to call event E1 the event that the committee has a sophomore on it, and E2 is the event that the committee has a junior on it. And so we're asked 3 questions on this. So are the events E1 and E2 independent? Is the event that a committee has a sophomore completely independent from the event that the committee has a junior? And if you just want to type yes or no in chat, and we can kind of talk about it, just your ideas. Are those 2 events independent of each other? Okay, so we've got 2 yeses. Anybody else think, are these events independent of each other? Okay, somebody else says no. What about anybody else? Yes or no? So yeah, so the last explanation, so they said no because if there's a junior, then there's less chance for there to be a senior, and that's kind of the correct argument. And the way to easily tell is there's only 3 people that can be on the committee. So if event E1 happened, like for example, it cannot be the case that let's say. So we'll have S will represent the sophomores and J will represent the juniors. So if we have a club with 3 sophomores, event E1 happened, but event E2 cannot happen. Right? You can't add another J to this because it's already made up of sophomores. So these are actually dependent dependent events, and that's why if you're looking parts B and C make sense. And in this case, what we're looking at here, so the probability that E1 happens, given that E2 does not happen. So what's the probability that our committee contains contains a sophomore, given that the committee does not have any juniors? So anybody have any ideas? What would this probability look like? Our committee has a sophomore, but the committee has no juniors. Okay, so somebody's saying, so you've got one answer for part B. So somebody said it's 3 over 2 squared. So they're saying this is about a 0.75 probability. Any other guesses that somebody has for part B. Probability of that our committee has a sophomore, given that the committee does not have any juniors. Yeah, so for this problem, it's not quite this 3/2 squared. So let's think about it this way. The way that this conditional probability is we're asking the probability this event happens given this event already happening. So in other words, event E2 has happened. So what does that mean? Well, that means that the committee does not have a junior. So we're looking at the probability that so event E2 has already happened. We know that the committee does not have any juniors on the committee. So the probability that there is a sophomore that is on the committee is just 1. It's 100% chance this happens. And why? Because we know that the committee doesn't have any juniors on it. The only other option for the committee is to have sophomores. So any questions on this about why this probability is 1? All right, I don't see any yet, but if you haven't, just type it out. And then for part C is really similar, right? Part C is saying, what's the probability that our committee contains a junior, given that we already know the committee does not have any sophomores? So what would this probability be for part C? Yeah, somebody says 1 as well, and that's correct. Yeah. Why? Because in this case, we know that event E1 has happened. So our committee has no juniors, or excuse me, our committee has no sophomores. So it can only contain juniors. There can only be juniors on the committee. So the probability that it contains a junior is 1. It's 100%. Note that this is also another way to explain why these two events are independent. Oh, yeah, yes. Yeah, so there's a bar here. Yeah, sorry if you didn't see that. Yeah, the bar over E2 meaning that event didn't happen. And this is another way, seeing that these are both 1, this is another way to look at like why these events are not independent. Because remember, for independent events, the probability of A given B is equal to just the probability of A if A and B are independent. And this certainly, 1 is certainly not the probability that there is a sophomore on the committee in general. So this is another way to see why are these two events actually dependent upon each other. Oh, and so this is, the bar is just another way to signal, not this event happening. Yeah, good point. Awesome. So any other questions on this problem? Yeah, the horizontal bar. Vertical bar is just conditioned on. We use it for conditional probabilities. The probability E1 happens given that, in this case, E2 bar has happened. Awesome. Okay, so we got a couple minutes left. Let's try to quickly go through this next one. I know we were a couple minutes late, so we might go a couple minutes over on this, but it's a kind of important problem. So here we've got a player on a baseball team, and they have a third probability each time they go up to bat of getting a hit, and a sixth probability of getting a base on balls. So they still get on base, but they get four balls each time they appear on the plate. And so this player, they have a contract that says that they get a bonus $1,000 each time they get a hit and $100 each time they get a base on balls. And they reasonably expect that they're going to have 600 plate appearances this year. I want to figure out what they should expect their bonus to be. So we're looking at expectation here. We want to find out what's the expected value of their bonus. So first, we need to figure out what the number of hits that they should expect to get. So out of their 600 plate appearances, what are the number of hits they're going to get? And what are the number of base on balls that they're going to get? And the one thing to note here that'll let this problem work is that each plate appearance is independent of the rest. Right? If they get a hit on one base appearance, their probability that they get a hit on the next base appearance doesn't change. Right? Because each time they go up to bat, they still have this constant probability of 1/3 getting a hit and 1/6 drawing a base on balls. So everything here is independent of the rest. And so that means, if you recall, when we're talking about Bernoulli trials, recall that the expected value for some random variable x, when the trials are independent of each other, is equal to n times p, where there are n trials. And each trial has a probability p of occurring. And we can only do this because each plate appearance is independent of the rest. So let's let h be a random variable. For the number of hits. Yeah, so somebody says, yeah, multiply that by 600. So yeah, the expected number of hits we're going to get is just going to be their 600 plate appearances. 1/3 of them are going to be hit. So as one would expect, there's going to be 200. We can also do that similarly. So let's let b be the event, or be a random variable for the number of base on balls. Then the expected number of base on balls is just their 600 plate appearances. 1/6 of them would be that. So we expect 100 base on balls. Then now we need to figure out what's the value. So we've got the expected number of hits, the expected number of base on balls. Now you need to figure out how much should they expect their bonus to be. So let's let x be the random variable for the value of the bonus. Right, and that's just, right, so we've got 600 plate appearances, and we knew that 200 of them, we expect 200 of them to be hits. So we can expect that she'll make 1,000 times 200 plus $100 times 100. And this will be $210,000. Yes, somebody says entirely too much money, probably. But yeah. So somebody asks, yeah, this is taking into that 600 into account. Yeah. So we're taking in the way to figure out this problem is you're just looking at the expected value, the expected number of hits and base on balls based on the 600 appearances. And we note that this works because in each appearance, they're independent of each other. The probability on one of getting a hit doesn't change over time. We're saying that it's independent of what happens during the last hit. And that's why we can make this. Yeah, somebody says baseball doesn't have a price cap. Yes. Yeah, so hopefully this helps you. This is, yeah, expected value can sometimes be a little bit tricky the first time you see it, but for independent events, it's not too bad, and it works similar to this. So yeah, so if you have any other questions on other things, please stop by our office hours, and thanks for coming to the discussion.